program. The second time was Genesis, which brought back samples of the solar wind. And then it was Stardust, which brought back samples of the tail of dust from the tail of an asteroid. And now OSIRIS-REx. And OSIRIS-REx is the most amount of material that we have brought back from outside the Earth since the Apollo missions. And so I was thinking, wow, what an honor to be part of this team that's going to do this only for the fourth time ever and from a different source. Quick reminder of where asteroids are. The great majority of them are here in green, and you can barely see it, but this is the order of Mercury, Venus, Earth, Mars, and Jupiter. And so between Mars and Jupiter in green are the great majority of the asteroids. Some of them can have their orbits perturbed by Jupiter and Saturn, and their orbits can cross or approach the orbit of the Earth. We call them near-Earth asteroids. Bennu is one of them. And I'll go back to that. So OSIRIS-REx went to Bennu, and we're so delighted. I'll tell you more. As a matter of fact, you can't shut me out. But we were not the first. The Japanese Space Agency, basically the smallest of the space agencies, was able to go to asteroid Itokawa and bring back a very small sample, it was micrograms, a few particles, but they succeeded. And then they refined their approach and went back to asteroid Ryugu. And they were at Ryugu when we were at Bennu, so we were exchanging, comparing notes, helping each other, and we have a formal agreement between NASA and the Japanese Space Agency, where they gave us 5% of their sample from Ryugu, and we're going to give them 5% of our sample from Bennu. But yeah, my hats off to them because they did it first, and they were very successful. Okay, so Bennu, our asteroid, was observed from Earth with radar. This is a radar image from which you get this 3D model. So we knew the shape, we knew the rotation rate very precisely, we knew the orbit very precisely, we knew the bulk density, we knew the reflectivity, which we call albedo. So that means that 95.5% of the light that falls on this asteroid is not reflected, it's absorbed. It's darker than pole. Pole is about 8 to 10% reflectivity, Bennu is 4.5. And spectral type meant it was primitive, but I'll go into that a little later. So the name before it got named by this contest was a very poetic name. 1999 RQ36. And I had to change that. So we changed it by, actually the International Astronomical Union, not the mission, changed it by doing working with the Planetary Society in the US, and they had a worldwide contest, and a third grader named Michael Puccio suggested Bennu, because Bennu is a mythical bird from the Egyptian mythology that comes out of the heart of Osiris. And so anyway, so that boy, who's now an adult, must be very, very proud that he named the asteroid. Okay, so here's the asteroid. And when we got there in December of 2018, we were ecstatic. We were getting all these images. We had been preparing for this for years. And so the rotation is, as we expected, 4.3 hours. Here it is with very large rocks on the surface that indicated that it's like a rubble pile. And so here's one of the biggest rocks. We don't quite know how it ended up there. Anyway, so I'll tell you a lot more about this. So we launched in 2016, got there in 2018, spent 2 years mapping it, sampled in late 2020, headed back to Earth, and we just got back less than 3 weeks ago. The analysis is taking place now, and then the NASA funding for the analysis will end, but I'm sure that there will be many other projects that will require the samples of Bennu. The analysis will probably continue for decades, for generations. Half of the sample that we brought back is archived for future studies. Half of it is going to be analyzed in the current project. Here's the orbits of the Earth, of Bennu, of the spacecraft. We sampled in October of 2020. And why do we send robotic spacecraft instead of human crews? And the main answer is that there are three factors, but because you can have a higher risk posture. There's no danger to astronauts. You can make them smaller, cheaper, and if something goes wrong, you're not endangering anybody's life. So human exploration is orders of magnitude more expensive. So examples of robotic exploration, the Earth orbiting satellites that study the atmosphere, the oceans, the weather. Here's one of the rovers on Mars. Here's the Cassini mission that studied Saturn, its rings, its moons. Here's the Juno mission that's studying studying Jupiter and its system. So robotic exploration is very important. It allows us to actually explore the terrain before the humans go. And then why do we bring back a sample? Because 95% of all meteorites are from asteroids. So we have samples of asteroids here. So why did we go to an asteroid to bring up a sample when nature was sending free samples to us, hoping that we'll go and buy more? And the answer is that the samples that make it to the ground are only 0.1% of what enters the atmosphere. In the two cases we've been able to measure this, the results are the same. The great majority of what enters the atmosphere will not make it to the ground. And we don't know what that 99.9% is. It could be the most fragile, it could be, we just don't know. So that's one of the motivations. Besides, we can make state-of-the-art analysis here on Earth that we can't send in a spacecraft. And as I mentioned earlier, future scientists will invent new instruments, and if we have those samples of pristine material that has not had to go through atmospheric entry and atmospheric contamination, it will be very important to keep it and make it available to future generations that may come up with new ideas, with new analysis, new analytical instruments. And this is the main part of the scientific justification for OSIRIS-REx. When the Earth and the Moon form, they form in what's called the magma oceans phase. It was a very hot phase where the surface of the Earth did not have any liquid water. It had liquid rock. So it was oceans of lava that covered the entire surface. As if there had been any organic molecules on Earth before this phase, they were all burnt. So as that surface cools and solidifies to form a crust, that crust is devoid of any organic molecules. It has none. So we know that asteroids and comets are rich in organic molecules, especially now that we brought back samples from Rivu and Bennu. And before that, we suspected that, and we said, listen, if we go to these asteroids, we will have a sample of the organic molecules that asteroids provided to Earth very early in its history. And that will help us understand a very important step, which is the step between complex organic molecules and the first living cell. We don't know what that step is. We don't know how life originated on Earth. And if we understand that step, we will have a better idea of not only the origin of life on Earth, but the possibility of life on Mars, the moons of Jupiter, planets around other stars. Back to the space economy. Asteroids are ideal resources for developing a space economy because soon mining asteroids for fuel, i.e. water, and other building materials will be cheaper than launching them from Earth. If we're mining for water, then we'll have the opportunity to mine for other things. But the water is going to be the one that subsidizes all the other types of mining. And so imagine if we also have not just water that gets sent from these asteroid mining operations to Earth, but if you have the building materials and you put them into a 3D printer in space that can print the structures of satellites like solar energy collectors or communication satellites, then you can build those things in space without ever having to withstand the gravity of Earth. So to have structures that don't have to be built on Earth, fold them onto themselves like the James Webb Space Telescope, put into a tube, shaken and subjected to a large G, and several times the gravity on Earth, and then delivered it to space to then unfold in a way that has to be flawless, otherwise the instrument will not work. So I think it's going to be much cheaper, not only cheaper, but we will be able to build structures that we can't even conceive of here on Earth because they will collapse. And again, when they're operating in space, they don't have to withstand 1G. So this is going to be revolutionary. So I think in the next no more than 20 years, this is going to be happening quite normally. It'll be the normal operating way in space. Back to Bennu. Just to remind you, the rotation, the rocky surface. And before we got there, we had a rough idea of what to expect. We had anticipated Ryugu to be about this size, it was, and about this shape, it was close. In the case of Bennu, we were even closer with the shape. We had gotten a much better radar observations, and we were able to predict its shape even more precisely. And these are the correct relative sizes between Ryugu and Bennu. And so we were rather pleased. As a matter of fact, we started to get a little conceited because, hey, we are so smart. We are scientists. And global properties, got them. Spin top shape, got composition, we got them. And based on previous observations, we expected areas of coarse sand or pebbles on the surface, kind of like the beaches in Progreso, right? And we had reason to do that. Here's an image of asteroid Itokawa where you see it's a rubble pile, but it has areas where there are not that many rocks. And so based on those areas, you can barely see them here, we had predicted that there would be coarse sand or pebbles in Bennu. Here's an image, one of the first images that we got that goes up off the surface of it. This rock is about 4 meters high. Okay, so, and these rocks do not look very attractive. I'm not going to walk barefoot on those. Okay, and so we had a little dose of humility from nature. We thought we had predicted everything. And that's what happens when we explore new worlds, right? And so no coarse sand or pebbles on the surface. Here's another images. Boulders everywhere. So we were able to identify some craters which were surrounded by boulders where maybe we could go down and pick up the sample. And the navigation team asked the imaging team that I'm a part of, can you get us an area of about 15 meters across to come in and sample, but no rocks? And we go, no 15-meter area without rocks. Oh, but the spacecraft is navigating so well, and we're so good, we can put it down in half this. What can you give us? And then we said, well, we've identified a few craters with rocks all around them. The biggest one is about 8 meters, but you're going to have to avoid all these rocks around them. They said, we got to change this. We got to change our approach. At that time, they thought they could use the laser altimeter to just come in, pick up the sample, move away, no hazards, no problem. They had to reprogram the spacecraft. Now remember, the spacecraft is already at a pendulum to the side of the sun. And they had to reprogram it to be completely autonomous. And as it descended, they needed to make corrections because it was getting too close to that boulder or too far in this direction. So we'll be making corrections to come, and we selected this site, which we call Nightingale. And I actually voted for this site, which had fewer rocks. But the sample people said, no. To us, this part of the crater looks much better for us to pick up the sample. So, and then the navigation people said, we can get there to the center of our crater and avoid all these rocks. We can do it safely. But so they uploaded the new program. They tested it twice. We did 2 trial runs and then the final the sampling run. And so we had all these finalists for our sampling place. We selected Nightingale, and this is an old artist conception, but I bring it up because it tells you what we, the scientists, were expecting. A relatively smooth surface without big rocks, where it was going to come down vertically and horizontally at a very low speed and move away. Now, we know that the surface was a lot rockier, but I wanted to illustrate how challenging this was because, go back for a minute. This thing is rotating, so we need to come down not only at a near zero vertical velocity, but the spacecraft needs to match rotation with the asteroid. And you're not in orbit, you're maneuvering with your thrusters. So, just to remind you that this maneuver that looks simple in the artist's conception, it was quite challenging. And we did it, and here's a set of images from the sampling. When we touch the surface, we fire a nitrogen bottle that fluidizes the dust, puts it into the canister, and then moves away. And I'll let it run a couple of times. So at the very last moment, the head of the mechanical arm adjusts itself to be completely parallel to the surface. We fire the nitrogen, and the conditions under which we sampled were better than any that we had simulated on zero-G flights here on the Earth. So we ended up getting more samples than we had anticipated. Our threshold for declaring victory was 60 grams. We estimate, and we haven't weighed our sample yet, that we got at least 250 grams. So several times more than the threshold. And we can, now that may not sound like much to you. It's millions of times more than the first Hayabusa mission brought back. It is 20 times more than Hayabusa 2 brought back. And we can analyze each one of these grains individually, and they tell us a different story of how they formed and what they were exposed to. Because the asteroid was never heated, and the grains were never homogenized. So we have just a gold mine of information with our sample. Let me then also tell you that those conditions were so favorable, and we collected so much sample that the seals of the canister did not quite close because they were completely full. And so a few particles were drifting away when we imaged the sample head the first time. And the head of the mission, Dante Laretta, said, we were watching all these images and we were watching some of these particles move away, and he goes, "There goes somebody's PhD fees." And he made the decision, let's stow and head back to Earth. And so we did. And the reason for that is the following. Before we sampled, the spacecraft extended its mechanical arm with an empty canister and did a rotation maneuver, and we measured something called the moment of inertia. And then we were going to do it again with the sample head full, and the difference would tell us the mass of the sample. So we wanted to know how much we couldn't wait, right? And he said, no, we can wait. I don't want to lose any more of those particles. Let's stow, head back to Earth. And so we put it in the capsule, and then we came back 2.5 weeks ago, and let me back up a little bit. We have an agreement with the Japanese Space Agency. They already gave us the 10% of their sample, and we're going to give them 10% of ours. The Japanese were so daring. NASA is very conservative, very risk averse. But the Japanese went to their asteroid, didn't waste too much time exploring in detail like we did. They go, oh, we can go down there and let's go sample. Wow! And they pick up their first sample. Oh, here, let's use our projectile. They had brought on board a projectile. So they set up this projectile thing, hits the surface, creates a crater, fresh material from under the surface gets exposed, they go down and sample a second time, and then they come back to Earth. A lot more daring than we did. They brought back less sample, but they brought back from 2 different areas of their surface. And here's, in the case of OSIRIS-REx, the capsule made it to the surface of the Earth safely. Here's the parachute. That thing was coming in very fast. You know, let's say I'm in OSIRIS-REx, and that's Earth. But it's rotating, and I need to shoot my capsule just at the right time for it to end up within this 10-mile ellipse on the surface of the Utah desert, right? So I head to Earth at the point where I can, the closest feasible point to Utah, or actually to the Earth. I shoot my capsule. So my capsule is headed to the Utah desert, and eventually will deploy its parachutes and all that. But then the spacecraft is also on a mission course to the Earth. So 15 minutes after the capsule gets released, it has to change course and head away from Earth. I'll go back to that. So when this thing deployed, for me it was a big sigh of relief. We're going to get this in. And so, in conclusion, OSIRIS-REx returned sample to Earth on September 24th. Bennu is a potentially hazardous asteroid, but it's also the target for asteroid mining. So its orbit is sufficiently similar to that of Earth, and it's relatively easy to go on and back. So it's likely to be one of the ones that we've done. And objects like Bennu and Ryugu brought prebiotic molecules and molecules such as water to the Earth, so they're going to tell us a lot about the very early Earth. And now, OSIRIS-REx is no longer. It's been renamed. It's now called OSIRIS-APEX. And it's in an orbit that will allow it to go to another asteroid in 2029. That asteroid comes so close to the Earth that, let's say, that is Earth, and the screen is the geostationary satellites for communications. Apophis is going to pass between the atmosphere and the satellites. It's going to come really close. We know its orbit so well that we know it's not going to hit us. And let me add this. Impacts from asteroids are something that none of us as individuals need to worry about. The chances of them happening during our lifetimes are so low that we don't need to lose any sleep over asteroids. However, big impacts that have wiped out like 2/3 of all the species on Earth have happened. One happened 66 million years ago somewhere in a place called Chicxulub. Anyway, and they will happen again unless we do something. So we need, as a civilization, to be aware of these. So OSIRIS-REx is going to be OSIRIS-APEX, is going to Apophis in 2029, and the team has already asked me if in 2029 I will help them with the images of the asteroid. I said I would be delighted. And I'm involved with other projects, but I quickly, when they asked me this a week ago, Saturday, I quickly counted. Oh yes, I can. Because I have other commitments between now and then, but they will be over. Anyway, so just to, if you wanted to follow the mission online and some of the discoveries, the capsule, this thing, got picked up, picked up, put into a chamber with pure nitrogen, because the capsule is sealed so that the atmosphere doesn't enter it and contaminate the sample. But that seal is good for about 40 hours, and we didn't want to take any chances, so they put it into this chamber with pure nitrogen. So if the seal ever broke, it would be only nitrogen and not oxygen that would go into the capsule. And remember, these samples have been out there in the vacuum of space. You give them oxygen, they're going to go, right? They're going to get all oxidized and changed. We don't want that. Anyway, and then it got flown to the Johnson Space Center. Last weekend I was at the Johnson Space Center, and it's, you know, the results are going to start coming out. The first one was that they opened the capsule and there was a ring of dust, black dust, in the capsule itself, outside of the canister. Probably from the fact that we touched the surface of a dusty, dark asteroid, and some material outside of the canister was shaken up, and because of all those vibrations, they accumulated into the outermost ring of the canister. And so I saw something in social media, mysterious black substance on the inside of the capsule of the OSIRIS-REx mission. Social media. We went to a dark asteroid that was dusty. And now, but for us it was a bonus. It was a lot more than we expected. Not a lot, but a little more than we expected that was in the canister. So I will entertain all the questions that you have. Thank you. Yes.
Doctor, first of all, thank you for the awesome presentation and for your service to national science. We really appreciate that.
My job and my pleasure.
My question is, so
Look at this, people will read my mind here in Mexico. Go ahead.
so my question is, how does Apex differ from Psyche?
I'm sorry, what was
How
the
does Apex differ from the mission Psyche that's going up? I think.
Yes, it went up this
It went
way.
up this.
Yes. Psyche is going to a metal asteroid. And the metal asteroid is probably the exposed core of a much bigger object, much bigger asteroid that heated up, differentiated because metal is denser than most minerals. Will concentrate in the center of the asteroid. The silicates will be in the mantle and in the crust. And then impacts will have openings. And this mission differs from Psyche or OSIRIS-Apex because it's going to an asteroid that is potentially hazardous, comes near the Earth. It is still relatively primitive, hasn't been heated up so much, but we want to study it not so much because of the science, but because of if we have to deflect it, we will know a lot more about its density, its rotation, all these details that will determine how it will react to being pushed. In the case of OSIRIS-REx, when we touch the surface of Bennu, the mechanical arm had a spring that once we touched the surface and the surface was solid enough, it would compress the spring and push us away. That spring never compressed. Luckily enough, the spacecraft was programmed that if the spring didn't compress, it would fire the thrusters and move away from the asteroid. And the navigation team tells us that had we not fired those thrusters automatically, the spacecraft would have buried itself. Those rocks behave like a fluid because gravity is so low. We didn't expect that. We expected the friction to be enough that it would push away from us. But this is our first time in a gravity that low. It's about 100,000 times lower than the gravity of Earth. And so all those nasty looking rocks, they just simply moved out of the way and allowed the spacecraft to do whatever it did. It's amazing. So when we explore, we learn. And nature makes us humble, right? Really rocking up the surface. I wanted to show you, if you guys want, there's a 3-minute video that was produced by a former student of mine in Spain. And she defended her thesis successfully. And at the end, she says, by the way, committee members, I have a figure to show you that it's not in my thesis. And I'd like to show it to you before we finish the defense. And we said, sure. And she showed us this. So, Felicia, no? Let me see if I have it here. Is that okay that I interrupt the questions? Okay. I think I figured it out, Felicia. I'm not completely the absent-minded professor. Well, I'm standing in the way. Let's try it again. It's not as bright as I'd like it to be, but I think it will be.
Not playing.
No, the image is not coming out. So we have a sound. And we have the tap band. So I'll tell you a bit more about this video. There we go. Gracias. So sunrise over Europe, there's Italy, Greece, International Space Station. Going by the moon. Passing Mars, and as you may remember, the majority of the asteroids are beyond Mars, between Mars and Jupiter. There's some effects that are being illustrated here that we just can't see because we have so much light. But the best part of the video is coming up. This was done in Spain, so it's in Spanish. And it's like now that's 1 million years. And it shows a little bit how the orbits of the asteroids in certain gaps that are affected by Jupiter and Saturn will be ejected from the asteroid belt. Dramatic music. So that's how asteroid families are formed in impacts. But look, the material doesn't just dissipate. Gravity pulls some of it back, and they will accumulate in a rubble pile, which is what most asteroids are. You saw the surface of Bennu and Itokawa, very rough, big rocks that are broken up. This is how they originate. And it was made at the Institute of Astrophysics of the Canaries, and by that company for Julia de Leon Cruz, who's Dr. de Leon now. She is now the head of the imaging system on a European spacecraft that is going to asteroid Dimorphos, which was hit by NASA's DART back in September a year ago. And the DART mission was a test of this technique to deflect an asteroid using an impact. It was hugely successful, and there's a collaboration with the Europeans. Europeans are building another spacecraft to do what they call a crime scene investigation. So they're going to look at the crater, at the rotation, at what happened to the asteroid, so that we will know a lot more about how much energy we will need to deflect future asteroids that could be headed towards Earth. Again, we don't have to lose any sleep over it, but somebody does, so that the Earth doesn't have the civilization on Earth doesn't get wiped out by an impact. Okay, so let's go back to questions. Oh, and I show this video to all my prospective PhD students, and I tell them, well, when they come, I would like to be your graduate student. I go, sit down, watch. And then I tell them, if you don't get at least an Academy Award nomination, you don't get a PhD. Yeah. And after I saw this video, I was on her committee. I've been working with her for about a year. I was spending my sabbatical year in Spain, and then she says, I have one more figure to show you. When the video ended, I picked up my jaw from the floor, and I said, that's a good video. It's like, wow. I mean, and of course, that kid is now head of an instrument on one of the European space agencies. Not surprising. Yes?
Do you actually share all your findings with other nations, or do you have a strategic advantage not sharing?
In the case of science, we share everything. We publish in international journals. We have peer reviews. Often are reviewed by scientists around the world. Sometimes just in the U.S., but often from around the world. I get asked to review things from Europe quite often. So the scientific community is quite open, quite international. There are certain things about the spacecraft that have export control, and it's a strange situation. For example, part of our team was Canadian. They provided the laser imager and other things, but mainly the laser imager, which was a huge advantage. The mission would have been harder without it. So I'm asked to work on a contingency plan with a Canadian colleague. What if our spectrograph were to fail? How would we try to mitigate that? And so I am reading all the specs of the spectrograph, and then I asked my Canadian colleague, listen, can you help me with this? However, I'm told that I cannot let you read these because you're a foreigner, right? And he says, very good, no problem. I wrote that. So some of these rules don't make sense, right? I understand that there's certain technologies that we need to keep in-house, but the bureaucrats sometimes, not sometimes, quite often. Anyway, so good, excellent question. Thank you. Please.
What is the physical size of OSIRIS? Its dimensions and its weight?
About the dimensions are about the weight of a minivan. So, without the solar panels extended. With the solar panels extended, it's larger. And of course, all of our power came from the solar panels. Yes. Yeah, it's a good one. Was that? Let me see if I heard it correctly. What would happen if that asteroid were to hit? Is that right?
Yes.
Is that the question? Okay. It would not be good. It would be, that impact would kick up enough dust into the upper atmosphere that would reflect the sunlight and cool down the surface of the Earth for several years. It would be a winter that would last several years and would go from the poles to the equator. So all of the vegetation would die, or just almost all of it. Civilization would collapse because we would have no food, and then civilization would just die away. Few people, maybe in bunkers, would survive, but imagining climbing out of your bunker, how I survived, and you look around, and there's devastation. Or there are a few hundred, or a few million hungry people that want their food in your bunker. What are you going to do? Kill the first 1,000? I know. So I am not one of those that would want to survive that, but it would be a person's different. Does that answer your question? Yeah, and tell her that even her, you do not have to worry about this. The chances of this happening while you're alive are nearly zero. But all of us need to worry about it so that our descendants don't disappear. So protecting Earth from impacts important. Eventually, we may have to protect Mars from impacts if we end up with a colony on Mars. Oh, we built a colony. What if there's an asteroid coming towards Mars? Right? So.
The RPM spending.
What? I'm sorry. What is
The
it?
RPM.
Oh, 4.3 hours is the period. So every 4.3 hours, it goes from noon to midnight to noon again. So the rocks on Bennu are heated and cooled every 4.3 hours to extremes, to 100 and some Celsius at noon to maybe close to absolute zero on the other side of midnight. And so the rocks expand and contract. What happens? They start to crack and they produce dust. So that's where we think most of the dust on Bennu is from cracking of the rocks. Please.
I'm not sure if everybody's aware, but like space mining is one of the fastest growing industries in the world now. And there's a few projects to reflect that. That's where all the movement is. With that said, where do you see the practical effects of space? What time horizon?
I'd say within 2 decades. And so his comment was that space mining is very fast growing. And in the case of, there's a country, the country of Luxembourg, has made space mining one of its priorities. And they're a small country, they don't have that many natural resources. And they became the brokers of Earth orbiting communication satellites. So all of the, if you want time on a satellite for a broadcast or for observations of this or that, you go through Luxembourg to get access to it. They became the brokers for that. And I got invited to Luxembourg to talk about the composition of primitive asteroids. And there are several companies in the US, some of them funded by Luxembourg, that are working on space mining. The University of Central Florida has a program on space mining. And so, by the way, I brought some pamphlets if anybody's interested about our PhD program at the University of Central Florida in physics and in planetary science both. And if you're interested in anything else, you can find me there and contact me, and I'll be glad to help. But the time horizon will be, what I anticipate will be the following. We're sending a lot of spacecraft to the South Pole of the Moon. There, we're going to be processing the soil in the permanently shadowed areas or the craters in the South Pole of the Moon, because the Moon's axis of rotation is not tilted like that of the Earth. It's almost perfectly perpendicular to its orbit.